Hi, this is Vector Formulation, and we're going to see a different way of looking at the general solution on this section as vectors, column vectors. So let's get started. The first step in developing the general theory for first-order linear system is to formulate the problem of solving such a system as an appropriate vector space problem. The key to this formulation is the realization that the scalar system of equations, which was given earlier to you, looks like this. Can be written as the equivalent vector equation as x prime equals a of t, that's the coefficients, x of t, that's the variables, plus b of t. If you remember, we had this a while ago, the way we write it. This variable x, the unknowns, is the green part, which is x1, x2, x3, all the way up to xn. So if you write this as a matrix of n by n, you could see it goes up to n. This is supposed to be xn, yeah. This is an n by n matrix times n by 1, a column vector matrix. That's my focus right here. We'll add up and we'll finish it. Let me show you what I have, so I will talk less and display the picture for you. This is what I mean. See this xt, that's the unknowns. Those are n unknowns, x1, x2 up to xn. It's a column vector matrix, and this is the whole thing about vector formulation. We're gonna look at the answers of x's as columns, not as displayed earlier. It's another way to look at solutions. So notice that x, x prime, and b are column n vector functions. This, and this. This is general introduction to the section before I start slowing down and focus on the main part that you need, guys, but I have to start with the general introduction. Notice that x, x bar or x prime, and b are column n vector functions. We let vn of I which is our interval, denote the set of all n vector functions on an interval I, and define addition and scalar multiplication with this set in the same way as for column vectors. Definition. Let x1, x2 all the way up to xn be vectors in Vn. So each one of them is actually a vector in Vn. Then the Wronskian of these vector functions denoted by w of x1 up to xn of t is defined by the following: the determinant of those column vectors. But you want to keep in mind that this is a little bit different than earlier, so we have to keep in mind what's going on. Remark: notice that the Wronskian introduced in this definition refers to column vector functions. Earlier we had x1 or f1 equals sine x, f2 equals x to the second. We used to go down and find derivatives. That's not the case right here, because every column is well established right here. We are not building columns, the columns are there. Okay, it's not the same. That's what I'm talking about right here. Determine the Wronskian of the column vector functions. Look at this, it's already two pieces, and this is already two pieces. So when you put it together, we get a 2 by 2. There is no derivatives involved. The determinant, as I mentioned, is e of t cosine t minus 6e of t sine t. Okay, that's how we do the Wronskian in this column vector formulation, not the regular way that we are used to. So if you have x1, x2 up to xmb vectors in Vn, W is non-zero at some point t sub 0 in I, then this set of vectors is linearly independent on I. This is the same example earlier. We have this. I believe this is non-zero, at least for when t equals 0. When t equals 0, sine 0 is 0. This would be gone. Cosine 0 is 1. A to the power 0 is 1. So it's 1 minus 6 times 0, which is 1. And it's not 0. At some point, as you can see right here. So these two column vectors are linearly independent everywhere. Example. Consider the homogeneous linear system of differential equations written as x1 prime equals x1 plus 2x2 and x2 prime equals 2x1 minus 2x2. Earlier we derived the following solution from the previous section, if you remember, to this scalar system. We came up with the following. x1 equals c1 e to the power negative 3t plus c2 e to the power 2t, and x2 was minus 2 c1 e to the power negative 3t plus half c2 e to the power 2t. We can reformulate this problem as an equivalent vector differential equation. Notice now that I'm slowing down, because this is exactly now the main part of this section. We know how to do this, but this section takes it further. Reformulate as an equivalent vector differential equation. Let's take a look. We have x prime equals ax, x prime equals ax, where a is 1, 2, 2, negative 2, and x is x1, x2. When we solved it, this is x1 and this is x2. Now notice if I play the game here and I split them, make them an addition between, and after that from this right here I take c1 out and I take c2 out from here, this is what I end up with, which can be written in the equivalent form: x of t equals c1 times what's left right here, and c2 out from here, and I see the half, and I see e to the power 2t, e to the power 2t, it's right there. This is mainly the whole idea of this section. Reformulate as an equivalent differential equation with different way of looking at the answer. So the set of all solutions to the vector differential equation is the two-dimensional V2I, spanned by the linearly independent column vector functions. Each vector is a column, and we have the answer. This right here. Now, playing the game, we came up with these two. That's this one here, and that's this one here. And that should do it for this section. And I will take longer from you. Just a main focus. I'm slowing down here so you could pay attention to this section and what it needs As you can see, I took my time to write clearly with colors, and I'm slowing down on the main part. As you could see, we're done. Thank you for watching. I hope that it was helpful. Hit the like button as always if you like it. Subscribe, comment below, hit the bell icon to be notified. Until next time, peace. JaberTime.